All right. So, um, so this is among the last sort of topics we will be seeing at the course. So please, I encourage you to just ask questions as much as possible. Uh, we'll just briefly recap what we saw yesterday. After that, I'll complete the proof of the theorem. But if you have some questions to begin with, then you can ask. Okay. Otherwise, I'll just start right now. Okay, so we are currently looking at best response dynamics, and this is because we were studying the behavior of a game. Now, behavior of a game in the sense that how people playing a game can sort of their actions may or may not lead to equilibrium, right? So that was the overarching sort of theme of this part of the course, that how to analyze game in terms of convergence to uh, equilibrium. Now, in particular, we started off by discussing a type of dynamics which is known as best response dynamics. And I said that best response dynamics is most sort of suitable for studying potential games, a very sort of a special category of game with a lot of nice properties. In particular, the property that these games always have pure strategy, Nash equilibria, something that all games need not have, right? So that was the so this question of what do we expect? Do strategic agents reach equilibrium? It turns out it is yes for potential games. And potential game in particular, what kind of equilibria they reach is the pure Nash equilibria. Now, it's sort of it deserves repeating that if you don't have potential games, then also this question still is valid, right? You can still ask that for any general category of games, what are the chances, or if at all, can we expect equilibrium to be converged to? But in that case, we might have to come up with other kinds of equilibrium. Our expectation for a pure Nash equilibrium may not be satisfied simply because that game may not have a pure strategy Nash equilibrium. Then some other type of equilibria becomes suitable. Okay, so this is where different kinds of dynamics are actually studied. So, as far as best response dynamics is concerned, we have sort of analyzed potential games and sort of use the existence of the potential function for such a game and analyze the behavior of the and use the behavior of the potential function in a way to derive bounds on how fast such a convergence might happen. So that was the point of answering this question. If so, how fast? Okay, all right. So briefly speaking, what is the epsilon best response dynamic? I will not, I'll just go straight ahead to this. Okay, this is, I took pictures yesterday just so that this is max gain version of the epsilon best response dynamic. Okay, so what is the, yeah. So what is the max gain epsilon best response dynamics? Well, as long as the game is in a is the current outcome of the game, or rather current state of the game, is not a pure strategy Nash equilibria, you would pick, in this case, it should become an epsilon is not an epsilon PNE. You will pick an agent I who has a unilateral strategy SI. Instead of an arbitrary agent I, what we would pick is an agent I whose improvement will be the maximum. So in other words, there might be multiple agents who have a deviating strategy which will give them a better outcome. Here, better outcome means cost reduction. Okay, so the potential games we are looking at are the ones which are cost minimizing. Okay, this is implicit in all the, I mean, I mentioned it yesterday, but today, right now, I didn't say. So please keep that in mind. We are talking about cost minimizing game. So an improvement means that by playing this strategy, my cost actually is sees an improvement. So in terms of this traffic, so congestion game, surface routing games, you can think of the time of delay. Look at the time of travel. There's an improvement in this. So instead of picking just any arbitrary agent which has who has a unilateral strategy, you would pick an agent I among all those who do have a unilateral strategy. Pick the one for whom the improvement in cost is the best. That's what it means by max gain. Okay. And you will move and you will update the strategy, the state of the game in that using that unilateral deviation, and adjust the cost of the agent in this way. Okay. CIS is before deviation, and you will find the agent I for whom this change to C prime S prime I, while all others remain the same, is the smallest. Okay. So this cost is smallest means the difference between this and this is the largest. So the improvement is the maximum. Okay, so that's a maximum gain over unit. Okay, so briefly, if you recall, the behavior of the potential function is this. This is a function phi, so that if any agent changes from their strategy I to I prime, okay, while all others remain the same, this is what this is. The difference in the potential function is exactly equal to the cost observed by agent I. Okay, so that's what we mean that potential function tracks the cost. So in this, if you don't have any, do you have any questions so far? Okay. So in this setting, we were studying this particular type of a game, an atomic selfish routing game. You have k agents, and you have a single source and single destination. And Ci is a cost function for agent I. Okay. In this context, we are going to see this particular theorem. So I've already said it is common origin and common, they have one single origin and common destination. The additional thing that we have is that the cost function has this jump condition. So for any alpha greater than 1, the cost function for every edge, CE, is a real valued function, a positive valued function, but that satisfies a property that the value of C of E with an extra load of x plus 1 ranges between the value of CE of x to alpha times CE of x. So in other words, if an edge had load x, now you give an extra load of one, meaning one player, some player who was not previously using this edge is now beginning to use this edge. The jump in cost, okay, the jump in load, the cost of the load would just see at most an alpha fraction of increase. Okay. And you will recall, I said this yesterday also, we are repeating that we are dealing with atomic selfish routing network. So it means each agent routes one unit of cost. These are not those negligible load agent that is a non-atomic setting where you don't even know how many agents are there and each one controls an infinitesimally small, let's say, load. Here, each agent has a noticeable presence. Okay, so when they change strategy, they basically route their entire unit of flow towards some other path. That's the setting. Okay, then in this case, we can prove that this max gain epsilon best response dynamic converges to an epsilon PNE in at most this many steps: k alpha by epsilon ln phi of S0 by phi of min. So phi of S0 is the initial state of the game. So phi of S0 is the potential value at that time, and phi of min is the potential value of is the minimum potential function value. Okay, and you recall that phi min then witnesses a PNE. Okay, that's it. Now let's just go over this definition one. This is the definition of epsilon PNE. It's an analogous approximate variant of pure strategy Nash equilibria, as I'm sure all of you understand by now. The only issue is to keep in mind is we are talking about a cost minimization game. Therefore, the inequalities, pay attention to them. Okay. In classical settings, we often say maximizing improvement in payoff. There it means you are getting higher utility. Here, improvement in payoff means reduction in cost. Okay, so that sort of thing. So as long as there are no players, or rather, this is the definition of P&E, that for all players, all possible strategies available to those players, the cost and seen by the player when he deviates to a different strategy, S prime I, while all others continue to play the same, is at least as much as 1 minus epsilon factor of the original cost. Okay, that's what, if there was no epsilon, if we were not talking about epsilon P&E, we were just talking about normal P&E, we would say CI of this after deviation strategy should be at least like we would want to be at least as much as the cost to be at least as much as the current cost. Okay, so here the only difference is 1 minus epsilon factor. Okay, now any questions so far? Okay, so then let's start proving. Okay, I took a picture of this. Maybe we keep this lemma statements here, and then it might be a little easier, like it saves a bit of time, but let me maybe just write down. So the first step that we will show is at any time, there's always a player with high cost. Here, high means at least average cost. Okay, that's there is a player. If phi of s is the cost, is the current cost of the whole game in the current step, that's what the potential function represents. So then there is a player such that the cost he is encountering right now is at least phi s by k. This is what this lemma says. Okay, in every outcome, there exists a player I such that cost of I is at least phi s or greater than equal to k. And the proof is very simple, in part because we assume, just maybe it right now. Yeah, so I'm feeling a bit tired, really exhausted talking. So it would help if you're sort of asked questions. Otherwise, then I will not repeat unless it's things that you people already understand. All right. So,
fine.
sorry?
The max, you here it's an averaging argument where you say maximum is at least the average end.
Right? Yeah, okay. Okay, so let me just write though this thing, maybe this has been that. So over there I wrote the definition of potential function in the most sort of way that we operate on it, like the tracking property, that the change in the potential function is like the change in cost, right? But the potential function itself that is defined as, perhaps this is something you can recall, is this thing. Okay, does anybody remember what is the cost of S versus phi of S? Why that tracking property holds? Quickly. Do you remember that step-by-step thing, that mental picture we had? Initially, there was one person in the edge. Then I think as if the second person joins this, the cost increases, then the third person, and so on. Ultimately, FE number of people are using the edge, E, right? And therefore, so there's a step-by-step increase in this thing. So, okay, let's write this. This is this thing. It's almost formulaic. Okay, where FE is the number of players using path that contains E, correct? And so this is inside you have this, but when we are in edge, we do this. Okay, maybe I hope by now square bracket has become very common, but CE I, correct? This was the definition of the potential function, right? Okay, so it's easy to see. Okay, can you tell me what about phi s and cos s, which is, are they equal or there's some other relation between them? Quickly. Which is, are they exactly the same or there is a difference between them? Or there's a like a relation, one is greater than the other, or they have to be related, otherwise how am I comparing, how am I using phi s to capture the cost function, right? See, no, over here I'm multiplying, here over here I have summation of fe, right, times ce of fe, correct? Over here I'm just using ce of I, where I ranges from 1 to f of e, correct? So unless I is actually equal to f of e, unless f of e is 1, when f of e is 1, they are basically equal, right? If there's exactly one agent, then they are the same thing. But otherwise, what do we say? Cost of s should be at least the same value of phi of s, right? So from here, you know, cost of s is summation of cost of each of the agents. If all of them had valued strictly less than this is supposed to be a value, this, right? Using this, therefore implies there exists an agent I such that it's a bit difficult today. Okay. Yes. All right. So now lemma 2. You guys now have to help me out. Lemma 2 is both, this is kind of routine, I would say. Lemma 2 is both interesting and it says something. So can you all read lemma 2? Okay, let me just write it here. Suppose I represent, maybe the wording in this thing yesterday was different. Suppose I represents the player chosen by max gain variant of epsilon best response dynamics. Okay. And takes the presence of the children and I makes epsilon move s prime I, then the improvement in cost experienced by this player I due to his deviation is at least epsilon by alpha of cost of any other player in that strategy. Yeah. For all j. Okay. Is this okay? What I'm saying? So the first thing to note is the following. I can, if you ignore this alpha, if you ignore this alpha quantity in the denominator, right? The fact that I itself is the person who is who experiences this, the player I for whom this deviation is an epsilon improvement move, right? Itself means that the improvement of cost should be at least epsilon times whatever his original cost was, right? That's the definition of this thing. Okay, let me just recall, let me write. For any player who has epsilon, when I say epsilon move, I'm meaning epsilon improvement move. We have this definition that CI, others doing exactly the same. So CI. So the second point. Okay, let's write it that way. The way I wrote the CIS. Correct? This is it. This implies that if I open this bracket up, what does this imply? Please tell me. CI, I can take this thing from this one. Epsilon CI is less than equal to CIS minus CI. I. Correct? Okay. This is also some, so keep this in mind, one or the other. This is by definition. Correct? So let's assume in any situation, wherever we are, players belong to one or the other category. Either they have an epsilon move or they don't have an epsilon move. Correct? So the fact that for any player who does have an epsilon move, right, we can say that, so let's say case one, consider player J. So I'm proving this lemma, okay? I'm proving this lemma for all players. All I'm doing is categorizing the player in terms of, do you have an epsilon move or you don't have an epsilon move? That's it, okay? So consider player J who has an epsilon move. Therefore, this thing holds. C of S minus has an epsilon who for, I should say, concentration is J for whom S prime I is an epsilon move. Okay. Then for that player, I can say the following. This is less than equal to 1 minus epsilon of Cj of S. correct? It just so happens that the player I, by definition, the one who has the max gain, right? His improvement must be at least as much as this. Yes? Since I is max gain, yeah, his improvement is at least as much, correct? So at least this was the as much as. I think I'm notational inconvenience. Okay. Therefore, we can say that the player CI has this. Okay. So let's call it condition A. This is a max gain condition. Now, what did I write? Case 2. Consider a player for whom S prime I is not an epsilon move. Okay. So then, what can I say? It must be that this player change. See, they are all changing to the exact same strategy as prime I. Somebody is experiencing an epsilon move. Some people are not. That's the main thing to consider. Okay. Is greater than equal to, meaning the cost has not fallen. It remains, it is at least as much as the 1 minus epsilon times of his original cost. Okay. So let's call this so this is B.
Apply me some ways to go.
Yeah, sorry for the disturbance. Okay. So you have this condition for all those players who don't have an epsilon move. Now let's consider, so these are the only two categories of players that there are, those with an epsilon move and those without one. Now the point is, however, what is the effect of the epsilon move over everybody? All players. Can you tell me? So what this mean? Epsilon move is, let's say, not epsilon move. I should say, what is the effect of player I changing from Si to S prime I on all players? others. That's what I mean to say. Because whether or not it's an epsilon move depends on the way the situation of the current player is and how it is affected because of this. All we can say is some change has happened, implemented by one of the players. Question is, how does it affect all the others, right? Can you tell me how do we analyze this?
Ma'am, can you please repeat the last result, case 2?
Case 2? Okay.
Yes, ma'am.
So the definition of an epsilon move is this. This is the definition, right? Anybody who so the point is there is a lot of I and J's floating around, but all I want you to do is understand qualitatively what the formula equation basically means. This just means that by the hypothesis of the lemma, somebody has shifted to S prime I. Okay. The player who has shifted to, rather the game has shifted, the dynamics of the game has shifted from S, state, to one player switching to S prime I, correct? The player who switched it is the one who experienced the maximum gain. Those are the hypotheses of the lemma, correct? Now,
Yes, ma'am.
this switch is obviously beneficial for this player I. We are trying to understand, is it beneficial for other players or not? Okay. So for any player for whom this is a beneficial move, so I'm saying consider a player J for whom S prime I is also an epsilon move, right? So for them, this is the definition of an epsilon move, correct?
Yes, ma'am.
Okay. So now case 2 basically just says if you are a player for whom this shift from S to S prime I is not a beneficial move or is not an epsilon move. So all we are saying is this inequality gets switched. That is what B is. See, for the player J, everybody else remaining the same, he has changed. So remember, S minus J means everybody continues to do the same thing. Player J is changing their strategy, and the J is changing the strategy to S prime I. Then the cost is at least 1 minus epsilon times the cost of the original before deviation.
Is strategy S prime I available to J?
So the point is, remember, this is atomic route. It is selfish routing game. The point is, we are all, think about again traffic routing. We are all on a path. We have all chosen our path to travel from point A to point B. All of us are traveling from point A to point B. We all have the same source, same destination. But there might be multiple paths to get from this source to this destination. Okay, that is why we say single source, single destination. Now I am traveling on my path. You changed your route. Okay, maybe your route, your path that you're taking now intersects with my path. We share some common edges. Okay, then I see additional load on those edges, right? Because now you are present. You were not there before.
So one comment, just from the fact that our paths
Your voice.
have some non-empty intersection.
Wait, lot of what you said got lost. Repeat it again, please.
Yeah, I'm so sorry. So the fact that our paths are crossing means we have a common strategy, right? Like,
we have a common
crossing paths implies common strategy. Like
not common strategy. This is the other things. Imagine that those diagrams you may have forgotten. So let's say this is source, this is destination. Okay. So
yes,
this is one path. Okay. This top is also one path. Okay. How many paths do you see from S to D? 1 path, 2 path, 3 path, so 3 path, 4 paths, right? Oh, actually many more than 4 paths. See,
There are like
1,
lots of them
this is,
from S to
yeah.
D.
So, but they're all from source S to D, correct? Now, whoever takes this path, suppose, so somebody was going via this path, okay, this top path, okay? And some people were going by this path, this middle path, correct? The person who was going via this top path has now decided to shift to this. So the people who are already traveling on this path, will they not see an increase in load and therefore traffic delay?
Yes.
That's the point. So the fact, think about people traveling via, let's say, let's maybe draw some picture. Okay, all right. This is one person, agent 1. This is also agent 2, okay? Maybe this is 2 and 3. This is 3, let's say. And this is 4. Okay? Yeah? Agent 1, 2, 3. This is 4. Okay? Now, let's say this switch is this agent 1, okay? Agent 1 has switched from whatever he was, P1, to now switch to this path P2, this middle path, okay? Therefore, agent 2 is basically sharing his whole path with agent 1, correct? This entire path P2. But the third player, he's only sharing this path only for this edge. Rest he goes on he moves. He came via this, then this middle edge is where he sees 2 other people. Previously, he saw only 1 other person. Now he's experiencing 2 other people, and then he moves down here and here. But agent 4 remains like this. Okay. So in this example, at least, you see one thing, which is that agent 4 has no change whatsoever. Correct? So due to agent 1 changing from path 1 to path 2, agent 4 sees no difference because he was going via this and he still continues to do this. But agent 2, 3 see an increase in load. Let me say congested. Okay. Yes. Now, you may ask in this example, why did P1 actually change from this path to this path? Dipra, are you still with me? Or did you get disconnected?
Uh, Actually, I did not understand the notation in that equation.
Which
Uh,
equation?
B. I think the left-hand side should be Cj S minus I.
No, this notation, Satya, represents that player J is deviating. J was traveling by some path, but now it has opted to move to path S prime I. That's what this means. Okay, let's see the statement of lemma 2 first and foremost. Okay, lemma 2 is analyzing the situation that this algorithm, this max gain algorithm, it was in state S. Okay, some state here means people have adopted some strategy, different players have adopted different strategy. we are talking about atomic routing game, so it means players have adopted paths to travel from the same source to a destination. That's what that picture was trying to explain. Okay. Now, at any time, the algorithm analyzes whether the current situation is actually an epsilon PNE. If it is not, then there must be some player with an epsilon move. Okay, just give me a minute. Okay, we are analyzing the behavior of this algorithm. The fact that the algorithm updated the state with respect to this agent I means that among all the players who saw an improvement, if this new unilateral deviation was taken, that is, somebody moves to that they see, we are talking about unilateral deviation. The question is, does player 1 have a unilateral deviation that gives him an epsilon improvement? Does player 2 have an epsilon move? Does player 3 have an epsilon move? This is the sort of question that this algorithm is analyzing when we do this, while current outcome is not an epsilon PNE. Okay. So now the point is, multiple players can have an epsilon PNE, may have an epsilon move. Max gain will choose the player for whom the cost improvement is highest. Okay. We are analyzing that point of the algorithm's behavior in this lemma. So this is why I wrote that suppose I represents the player chosen by the max gain epsilon BRD, such that, and I makes, so there exists an epsilon move. So let's say the change of move is S prime I. Okay. Now, what we are analyzing is how good is this move S prime I? It is obviously very good for this agent I. But notice one thing. S prime I has a path. Oh, I think I understand what the issue is. Is this the question okay. See, here strategies mean, or actions mean paths. We have stated again, and I have stated again and again, that we have the same source, same destination. Therefore, every path is available to every player. So if S prime I is an epsilon, is an improvement move for a player I, it obviously means it's an action that player I can take. That also means it's also an action available to player J. Okay. I'm sorry. Okay. Okay. Is this the confusion, Satya? When we say strategy, I've been using the common or generic terminology we always use for all games. What we are talking about is choice of paths. So S prime I represents a path. Okay. Let me write this explicitly here. S to T path. Oh, I don't want to use S. I remember why I said it's like origin and destination. Okay. I don't want to create confusion, add more. Okay. This is a path because all agents are traveling between the same origin and destination. For each of them, this path is also available. The question is, does this actually give them an improvement in their time? Okay. If you keep that in mind, now case 1 is just saying that this is a player J for whom this change in path actually gives an improvement. And case 2 is a player for whom this choice of path S prime I actually does not give a time of improvement. That's what this is representing. This player's travel time now, given that somebody has that if he were to shift to this path instead of in whatever path he was traveling before. Is it clear now? Please tell me.
Yes, ma'am, it's fine.
Okay, I'm sorry. So this is the example. Maybe I should have written before. So see, between here, this is same source, same destination. All paths are available for all 4 players. For whatever reason, they have chosen to split this way. Okay, so player 1 was traveling via the top path. Okay, this one. Player 2 and 3, 2 was going via this path. Okay, 3 was traveling via this path. Or rather, let's say this. And player 4 was traveling by this bottom path. So essentially, each one was actually taking 4 different paths. Some of the paths had some overlaps, right? Some edges they were sharing, path 2 and 3, but all 4 of the players were actually on different paths. Okay. Now, for whatever reason, I'll tell you, we can assume as if the cost along this path, okay, is very high. In particular, this is a very high cost edge. It's possible, right? Therefore, player 1 thought, I can shift to this path, right? The second path, basically just completely avoid this edge. Say this is a cost edge. Okay, this is why player 1 decided that, okay, I can move to, there's a better move for me to just go here and then shift to this path. Okay, so compared to what he was before, which is traveling via this edge, he actually sees an improvement, even if there are 2 other people already using this edge. Okay, but for player 2 and 3 who were using this edge to travel, and this 3 was using this, for them the presence of player 1 may have given rise to an increase in time travel in time. Okay, this sort of thing can happen. Sorry, I needed some coffee. Okay.
Yes, ma'am.
I'm sorry for this. Was this the cause of confusion? What this strategy S prime I means in terms of J? If so, then I'm sorry. I'm sorry. This is a simple matter. It's just that these are representing path choices, and all paths are available for everybody. This is where the single source, single destination assumption is so important. Okay. Okay. Now that I have said this, let me revisit 2 points and say something else I might just forget, which is that the statement of this theorem, okay, this particular convergence property, the number of steps, it crucially depends on agents having common source and destination. Okay. And this sort of a jump condition, they are kind of neat. So let me just say, for the moment when we have arbitrary agents who might have different source and different destination, and therefore their strategy spaces are very different. Okay, for those kinds of games, we can't show such good convergence rate. We can still bound it, but this convergence rate does not hold. Okay. All right. And this jump condition, if I loosen it, then this is also necessary to bound by this thing, the number of steps. What I can do is the following. Instead of just defining this max gain dynamics, this best response dynamic in terms of the max gain variant, that can be tinkered with. And there are other variants that one can have, but assuming these first and two conditions remain the same, you get similar bounds. Okay, so I'm not going to be able to prove all those other variants, but perhaps maybe we'll see. Okay, so it's not going to be part of the class, but if you're interested, I can tell you about it later on. Okay, so this is why this is important to note that we are talking about the same source, same destination, so all players have the same paths available to them. This is why I can see S prime I can analyze S prime I, the choice of this path, in terms of how it affects every player in the network. Okay, that's the implicit this thing behind case 1 and case 2. Okay, now, so that brings me the question, if so, consider states as I guess this is okay versus is Diplo back? What is, did he get disconnected? So what should we do? Should we proceed? And then, okay. All right. So once the pro is back, okay, let's see. We'll talk to him separately. Okay. So let me just proceed. Okay. So S hat represents the situation when the player I has moved to this, has undertaken this deviation. Okay. This is what I mean by S minus. Originally, everybody was in the state S bar, right? And then player I has deviated and chosen this path S prime I. Compare there to this situation, which represents the case when J has opted to take this path S prime I. Okay. So, and J is like a generic player, like anybody, not the max gain player. Okay. All right. So, can you tell me what is the difference between S hat and S tilde? How much do they differ? There
All
are
but
K,
two.
all but two. Okay. So K minus 2 agents are the same, identical, correct? Yes, good. K minus 2 agents are identical. What about the other agents? Sanjay? See, somebody is using S prime I. Question is player I using or player J using? Correct? Maybe I shouldn't have used S prime I should have just used S prime. But okay, hindsight is 2020. But please don't get confused. Try to qualitatively understand the underlying phenomena. Okay, so if you just try to understand the equations, it's just like you'll only get half of the picture. So the point is K minus 2 are identical. S prime I is being used in this strategy as well as this. S prime I is being used by one of I or J, correct? Therefore, K minus 1 strategies or paths, let me call, are identical, so rather, let's say, are same in S hat and S tilde. Do you agree? K minus 1 paths are the same, right? Okay. So somebody shifted. So let's go back to this example. somebody shifted, right? In this particular example, player 1 who was going by this has shifted from this path to this path. So the jump in load, jump in cost across the path, especially actually across this edge. This is the only edge. Actually, a player, this edge also sees the increased value. This edge as well as this edge, right? This edge, this. These are the things that are now being used by player 1, was not being used before. But either way, across each of these edges, there's an increased load of 1. Yes? Therefore, by the jump condition, the cost can only rise by an alpha factor. Yes? Please tell me yes, no, right, +1, something. It's very disconcerting to just...
Yes, ma'am.
Okay. Very disconcerting without getting any feedback. Okay. All right. This is why, due to...
Cost
so this
decrease. Cost doesn't increase by alpha means it's a number which is less than 1 and your cost is decreasing.
so the cost per edge is a property of the routing network, right? This condition.
So what is the alpha jump condition?
Yes. This thing. Consider a selfish routing network with all agents having common origin and destination. For all alpha greater than 1, cost function, actually it's for not all, for a given alpha, it should be, okay? It's for a given alpha. We are considering a network where the cost function defined over the edge costs, okay, satisfies this property. CE of x plus 1 is at least CE of x or no greater than alpha times CE of x. Think about CE of x being the cost sort of witnessed by the edge E due to x units of people using it. Now one other player comes in. The cost can only, it's a property of the cost function.
Okay, fine.
Okay.
Thank you.
So I'm using the word cost in various avatars. Cost for edge, that's what I was just now saying. Previously, I was talking about cost for the players. Okay, so this is, if you can, please stop me and ask, okay? So to go back to this, k-1 paths are same between s hat and s tilde. There's only one path that is actually witnessing a change. Okay. It is possible that certain path was not even used before and now suddenly it is being used. It's possible, right? Before that, its cost was 0 because there was 0 load on it, and now it has cost is it sees 1 unit of load. Either way, does not matter. We know what the alpha jump property says, that when the increase in load is by 1 unit, then the jumping cost is alpha times whatever was the original cost. Okay, all right. Okay. Due to alpha jump condition, we can say that the cost, see, J is the player who may not be J is an arbitrary player, not necessarily one which has epsilon move. Okay, so we can say regardless, the cost in the new cost experienced by the player, sorry. These are probably tiny things that I often don't pay attention to by changing the order of this thing, but if it helps to clarify. So the cost of J when S prime I has been moved to, like he uses this thing, it is at most alpha times whatever the cost of I is when it makes the move. Addition applied to the path unit. Is it clear? If you're confused,
Yes, ma'am.
somebody said something? Ankit? What was your question? Can you
Yeah, ma'am. I understand.
Okay. All right.
You asked, yeah.
There's a lot of internet problem today, but at mine it seems somewhat standard.
Yeah.
Okay. All right. So think a little bit about this. The main point is that due to this path, due to this unilateral move where only one path is getting changed, the increase in load can only be by a factor of alpha. The increase in load is by a factor of alpha across all the edges on that path. Okay. But across the path that is like that we are now seeing. But that path, so I mean, it can be a very complicated network and so on and so forth, right? So for example, here, this part was already seeing 2 units of load before, player 1 and player 2. It continues to see, nothing changes. This one was initially seeing only 1 unit of flow because player 2 was using. Now it sees player 2 and 1 using. This edge was being used previously by only players 2 and 3. Now 1, 2, and 3 are using. This edge was being used by only player 2. Now player 1, and 2 are using, right? And this was being used by 1 and 2 both. So all sorts of things can happen. But either way, all we know is that when we compare the cost due to this change, I is the player for whom this is a beneficial move. J is any arbitrary player in the game. He may not, J could also be a player who does not see but this is not an improvement move. But no matter the cost, no matter what is the case, his cost cannot jump by more than a factor of alpha as experienced by the best gain player or max gain player. Okay, this is what this is. This is C. Now, can you tell me what can we, if you look at A, B, and C, what can we say? Is there a conclusion we can draw? Quickly. Okay, so let me say this. I claim if I combine A, B, and C, let me just repeat the gist of this argument again. Okay, A represents a player for whom this is an epsilon move, moving to S prime I. 1 unit of flow, moving 1 unit, shifting to S prime I. A represents one such player. B represents all those players for whom this is not a beneficial move, not an epsilon beneficial move. Okay. C captures the effect that this move has on the sort of the relative effect it has on any player in the game, whether the one that has an epsilon move or not. Okay, this is an upper bound. All we know is that right hand side here, Ci represents the cost of a player who has the maximum gain. Here, J could be any player. The one with an epsilon gain, one without an epsilon gain does not matter. In comparison to the player with the max gain, his cost can only increase by at most an alpha factor because of the way the cost function on the edges are. Okay. So now what can we say? So using B, I know that Cj is greater than equal to 1 minus epsilon. Okay, sorry. I have to be careful with the inequality. Let me just copy this. This Cj. This is inequality B. Okay. In comparison to Cj, using the inequality C, I know it is alpha times Ci, the most improving player. This. Okay. Now, but A actually tells me how good is I's improvement, right? Player I's improvement vis-a-vis what he was before. So that is this thing, alpha times 1 minus epsilon Ci of S bar. Okay. I just combine B, C, and A. Nothing else. What do I get? This quantity and this quantity, if I can cancel, okay, what I get is this. This is this. So it means that the cost of this player, cost of all those players, right, an arbitrary player J, their cost in this thing S, in the original strategy, can only be at most alpha of the cost experienced by the max gain player from the initial strategy, from the initial state. That's what this means. Correct?
Is this true for any J or for the J
Yes.
for which it is not an epsilon move?
It's for any J. See, when I said, so, okay, so this is A represents a player, equation A represents a condition for all those players for whom the shift to S prime I, think about 1 unit of somebody moving to S prime I, okay? This path choice may be an epsilon move for multiple players. That's the situation represented by equation A. In particular, that player could be the max gain player whom this algorithm decides to, next step, the switch in state would be with respect to the max gain player. But multiple players can actually see an epsilon move, because when we say epsilon, so epsilon could be so small that for multiple players, this is an improvement. But The max gain player is the one who sees the maximum improvement. Okay. For all those players for whom this is an epsilon improvement are represented by player A, are represented by equation A. And B are those players for whom this is not an epsilon move. It is not an epsilon improvement move. Okay. All right. I think I mangled some of the part of your question. So what we are saying is here J represents, sorry, I think I misspoke when I was trying to explain to you. But, so in this equation, J represents a player, all those players for whom this is not an epsilon move. Okay. Using B, we know we have this condition that their previous situation before the move is 1 minus epsilon less than whatever this new thing is that is. So this means they are not experiencing epsilon improvement. But equation C tells me, well, no matter whatever their situation is, it cannot be worse than alpha times the cost experienced by the max gain player. This is what this is. Now this quantity, the cost of the max gain player can already, we know, because he's a max gain player, therefore he is also an epsilon gain player, right? This quantity, his cost improvement is at most 1 minus epsilon of the original cost. Okay? And this is why this allows us to say what happens for all those players who are not experiencing an epsilon move and compare their situation to those players who are, to compare it to that player for whom this is the max gain move. Okay?
Okay, ma'am.
That's what this is. That's what this equation is saying. Sorry, Zaka. I hastily spoke when I said no. Okay? All right. So now we have this. What more needs to be shown? I mean, how far? I still need to show this, right? That this is an improvement. This quantity holds. Tell me. What? Okay, let's look at again this equation. Max gain, let's call this the max gain equation, okay? Or max gain condition. Not max gain, this is actually an epsilon gain condition. And therefore also the max gain condition. But it's at least the epsilon gain condition. So now equation A implies what? See, if you look at it, I'm just going to open it up and write, okay? It's say up minus, this is the this is equal to the epsilon s. See? Just by moving this sign on this side and nothing more. Okay, so equation A is this. Now this quantity I can bound using equation D. Epsilon Cj of S bar by alpha. Correct? By what we just know. Therefore, see, this is the quantity that we had to bound according to the statement of S. Where J doesn't not epsilon. Correct? Agreed? Satya, somebody
Yes,
say.
ma'am.
Okay. Now, moreover, see, for any player J, okay, some other player that is, for whom S prime J, S prime I is an epsilon move, I already have this condition that CIS this is the improvement of max gain, right? By max gain player. This is at least as much, because this is by definition maximum, right? The gain enjoyed by this jth player, right? This is by definition of max gain, which this is more than epsilon Cj. Yes. This is correct. Sorry.
Yes, ma'am.
Therefore, for any alpha, since alpha is greater than 1, obviously this quantity is greater than epsilon by alpha Cj of S. Correct? Yes. I don't know. Maybe today it was my concentration or internet connect. I don't know. Maybe it didn't have to be. I hope I didn't confuse you all too much.
Yes, ma'am. If alpha is at least 1, then last equation is fine.
Correct? So for both category of players, ones for whom this is an epsilon move, ones for those that this is not an epsilon move, for both cases, we have proved the condition for the hypothesis of lemma 2. Correct? This is when you need epsilon by alpha when J is actually a player for whom this is not an epsilon move, the shift to S prime I. When shift to S prime I is an epsilon move for some player, right? You don't need this the epsilon by alpha. You can show a better improvement. That's what this epsilon by CJS is represented. And because alpha is strictly greater than 1, this quantity itself obviously is greater than epsilon by alpha. Okay? So, therefore, lemma is proved. Guys, please, I'm going to share this thing with you all right away after I'm done. Okay? Writing. Please go over the notes and see if you go over the notes, your notes, even better if you have. Please see and try to sort of go over it and ask your questions, okay, by next week. Because you'll have your exam at the end of this week. Okay? So now, quickly, so lemma, using lemma 1 and lemma 2, we will prove the theorem now of theorem. What are we proving? Number of steps to converge. Here, number of steps means a number of iterations, right? Not the number of steps that the algorithm goes through, the number of times the algorithm will keep on making some move. Is what? Tell me, what do I want to show?
We want to show that the summation of changes in potential function is the difference between what we converge to and our initial state.
Okay, so we want to basically show the bound that this is the number of steps to converge is exactly this, right? Yeah? Okay. So now, how are we going to show this? I gave you a basic proof of argument, how to think about these things, that if I need them to converge, if the algorithm has to actually find this many things, then I need a bounded chunks of improvement every so often, right? That was the idea yesterday, the block diagram. So now you all complete the proof. Tell me, how should we go about? So what? If you want to see the statement of lemma 2, you can see. This should tell you, okay, let's start. I'll give you some hints. It's very easy once I set it up. We again, as you said, we want to see how the potential function, this is why the potential function is so helpful. Without this, I don't know how we would analyze. I mean, this analysis is sort of, customized for the potential function. So what do we know? We know that improvement, change in the potential function value from step to step. What should I write here?
Is equal to change in cost function.
Very good. So I can write, this is literally the definition of this function, right? The potential function. Then now use these lemmas that we have proven. What did we just now show? See?
The change is at least alpha by epsilon by alpha.
By alpha. Correct. So this is at least epsilon by alpha of CJS, right? CJS, where for all J, correct? Yes?
Yes.
So if it's going to be for all J, I might as well take the J for which this CJ quantity is maximum, right? Maximum among all the players. Correct? Yeah. Then now the first lemma should ring a bell. This is the max cost player. We already know that there exists a cost player. There exists a player whose cost is the average of the potential function. The max player's average value can only be higher, right?
Yes.
So phi s by k. Correct?
Yes.
I'll show you the statement of lemma 1. See, there exists a player I such that either this player itself is a max player, or the max player's max cost player can only be higher value, right? At either way, we have a lower bound of phi s by k. Correct? Okay,
Yes.
so then what else is there? Is anything there to... So basically, therefore, let me just this. Therefore, basically the potential change is this. Epsilon alpha k. So if I just change this, does this seem easier to interpret? What? See? What are we saying? That I should have written, let's say at ith, whatever, at any iteration. So at any iteration of the max gain algorithm, this is sort of the improvement you have, right? That the phi of S, therefore, each step, phi of S falls by a factor of. Okay, I would like the undergraduate students and the master's student. I know what Satya and Sanjay know and Mohana, so I'm asking all of you, have you all seen an analysis like this? Do you recognize this? Nobody's around?
No, ma'am.
All of your voices are I heard a lot of garbled sounds. Did you guys hear Sanjay, Satya? Did you all hear them clearly?
Both, I mean, Ankit and Malay were speaking at the same time, so maybe one by one, if they respond, to
Okay,
be clearer.
yeah. So Malay, speak first, please. Have you seen an analysis like this? Okay, it's very garbled, so I'm going to talk. So I will talk later. Maybe the internet connection is too bad. What about you, Ankit?
No, ma'am. So far, I haven't seen this apart from the assignment questions.
Okay, so when I say this sort of analysis, I don't mean that potential function type of analysis. Maybe you have not seen it. Maybe you see if you have done amortized analysis, right? There we do basically same things, but maybe it does not ring a bell right away because we don't usually do amortized analysis all the time. You usually do it sort of worst. So amortized analysis, there's a component which uses potential function and so on. So that aside, this sort
Network
of thing,
flow.
yes, of course. This is what I'm saying. Like these things show up in many different guises. So you may recognize one, but in a different form, not the other. So, okay. I hope this is clear. If not, you're more than welcome to come back and ask me, Sanjay, anybody. Okay. So this is that. But I'm saying this part where we are saying is that you have a quantity. At each step, I shave off a certain factor. Okay. This is a very standard idea. Just think of it like in terms of binary search. First, you have a one whole array, right? You find the midpoint, you do a comparison, and you're able to discard one entire chunk of the array, right? So now in the next step, your input solution basically is of size n by 2. Next step, it's half of n by 2. So it's n4, then n by 8, and so on and so forth. It's basically a similar idea that we are doing here. The value was phi of s at the beginning. Then we shaved, each step is shaving off this much factor. See, this is less than 1, right? 1 minus epsilon by alpha k. As long as this epsilon by alpha k is a non-zero quantity, what you're doing is shaving off a fraction of the potential function. Okay, so the point is, how many steps can you go till this value phi of s, till you're able to shave off a constant factor? So each step, I'm taking away this. I want to solve for L such that this thing is equal to some constant. Okay, this is the question I'm asking. This has a simple answer. If L is the reciprocal of this quantity, okay, alpha k by epsilon, then this basically 1 by this quantity, okay, that's what I'm writing, is equal to, let's say 1 by this system. You may know this fact that 1 minus x to the power 1 by x is less than equal to the into the power minus x. This is correct, right, guys? Yeah. This is basic bread and butter. I don't remember too many inequalities. I tend to remember this one. Okay, it's a very basic thing that we use. So this is it. That's why I'm saying that if I do for each this many number of steps, iterations. Okay, this many again iterations and so on and so forth. Phi s falls by factor of 1 by e. Okay, end of each block. I want phi of s, rather, initially we start by phi of s0. I'm trying to get to phi of min because this is what represents the PNE condition, right? So how many blocks do I need to go to actually get to this? Very simple arithmetic, I think. I don't know, arithmetic only, algebra and so on, but point is, if I think of it as phi s0 by phi min, if I take the ratio of it, what do I get? Let's say they divide exactly, okay? I get this value beta, which tells me how many times phi min divides into phi of s0. So starting from phi of s0, to get to phi min, I have to shave off this factor beta, correct? That's the point. To get to phi s0 to phi min, I need to shave off given that each of these blocks tell me that I am able to shave off a constant factor, 1 by e. So how many blocks would I need then?
Number of powers of 1 by
Number of powers of
1 by e to get beta.
yes. So in other words, it should be ln of this phi s0 by rather ln of beta, right? Yeah. Correct? Number of blocks. Therefore, total number of iterations would be the number of iterations inside each block times number of blocks. Correct? This is why this is this quantity. See, alpha k okay. So voila. Okay, it's fine. We don't have to do more than we can understand, so it's okay. So I wanted to start, at least introduce you to min regret dynamics, at least do some compare and contrast as to why we use that and not this before we end the course. We will see next week whether it's I mean, I need you all to understand at least this much properly, okay? And if you don't have, ask question because the course is sort of about to end and so on. And we'll see next week if maybe we'll have the Wednesday class, okay? And then Thursday can be just discussion and doubt clearing and that sort of thing. Is that fine? So I just want to end this thing. So today we didn't get started. It's fine, not a problem. But go over this. If you have any questions right now, you can. But else you can ask me later on. Okay. All right. Oh, so I guess he didn't come back. Satya, can you stick around for a little bit if you don't have any other class later on?
Yes, ma'am.
Who else is? So Malay, Ankit, do you all have any questions now, or else you can ask later? I guess it's fine. Okay then. Okay, Sanjay, Mohana, all of you guys can also stick around. It's not a problem. They have classes, so yeah. Okay. So 29th will be the exam. Okay. So 29th is what day? 29th is Friday. Okay. So maybe 28th can be a doubt, we clear doubts and so on and so forth. We don't have to, like, I don't have to teach something new until the end, right before the class. So you guys tell me, was this difficult? I don't think, I mean, what was it difficult?
I have seen it before in an analysis of network flow, but
You mean
like whenever
potential,
I do it, it takes time.
you mean potential function argument?
Not potential function, but this that
Load.
change is happening with a certain ratio.
Okay. No, I was basically asking about this thing where we are analyzing this sort of getting the basically not the proof of the theorem, rather the proof of that lemma. So I guess I should have started by not using the word strategy and all, instead of talking in terms purely in terms of paths and so on. It's like an old habit using non-standard game theory terminology, and then so I guess I did emphasize that there's a reason why we are using single source, single destination paths, basically. This is an important part of it.
Just want to say, you can stop the recording if you want. I mean, I
Okay.
just wanted to tell the media.
Yeah. This is off the record. Yeah, of course they have stopped the recording. They can stop the recording. So I'm assuming, okay, or they will just edit it out. Okay, so fine. I mean, this is discussion pertaining to the material only, so it's not an issue. So the point is, I guess that is one thing. The reason to emphasize this part is, of course, this is post mid semester, so this is an important part of the course where you will be tested in the exams. But that's sort of among the main concerns, but that's one thing. But secondarily, what I want, the reason I'm saying is that the potential function type arguments are very sort of very much a part of the algorithmic game theory toolkit. Much more so than than what we see in general algorithm. You understand what I'm saying? Like there are certain domains, online algorithms, algorithmic game theory, where I seem to see potential function type arguments much more than, let's say, general algorithmic analysis. Okay, so it helps to get used to this. Of course, potential function, finding a reasonable potential function it's sometimes almost a matter, like once a paper is written and the result is in front of it seems like magic. Like how could somebody have come up with this and so on? So there's a fair amount of creativity involved and so on. But once it is there, the description or the understanding, the analysis becomes fairly explainable, let's say. We should be able to see there should be a direct correlation between what is happening and the change in the potential function. So that's why the point of saying this, can you interpret reasonably what the inequalities represent? It's not just symbol manipulation. At least that's what I'm trying to do. If it's not clear, many people might interpret it differently or in a different language. You are most free to do so. But if something is just not absolutely clear or you disagree with what I said, then of course you should raise. Then of course, I mean, please come by and ask. Okay. I would like you all to take away this part. I mean, retain some of this well after the course is over. Don't not just forget, the day after the exam is done. Okay. So this is the point. Okay, then I'll see you all next week. It is Wednesday. We'll talk on Wednesday, definitely. Okay. And with that, we'll wrap up the course. Okay. See you then. Bye.